Okay, I guess we'll get started. Welcome who are live on the line right now. And to those who will be watching in the future as this webinar is being recorded. So I just want to start by reminding us on Friday we had an introduction to RGB astrophotography, that is taking images through the telescope using colored filters placed over the detector, and then using those three separate images to add together information coming from the blue part of the target in the sky, the red and the green, to create a what's often called a true color or representational color image of the object in space. And we did our alien eyes activity and our little astro poetry activity. So this week we wanted to basically cover some Q&A. So if you've been having trouble with anything, you can feel free to ask the question during this webinar. And also I should mention that after this webinar, Harry is holding office hours. So you can link into that right after we stop, and he can give you personal help. Actually, you can share a screen with him. You can do things together if you're having trouble with any of these. So I want to bring into the field of view here everybody's take a look at some of the RGB images that have been coming in, just so you can see, if you haven't had a chance, see some other people's work. Here, Carrie has says she's almost embarrassed, but this is a very nice image of the Ring Nebula. We'll see another one further down. I can just barely see in this image of Carrie's, which she clearly has zoomed in because there's some pixelation around the edges. There's a little red edge to this Ring Nebula, and it turns out that depending on how you do your processing of each individual red, green, and blue image, you can make that stand out a little more. We'll probably see it in an image down the way. Leslie has a great image, which I think she zoomed in software, not, she didn't ask for a telescope zoomed in image. She processed it and then zoomed in the JS9 window, and on the part of interest. The thing I really love about this image of the Orion Nebula is I don't know if you can see on your screen these 4 stars right here, and how you can tell that the stars are actually different colors. There's a lot more dim red stars than those white stars, and you can really tell that in this Orion Nebula, that like that star is very red, and there's a bunch around here that are yellower than these bright white hot stars right in the middle of the Orion Nebula. As we scroll down, I see Rick Sanchez has a nice Ring Nebula. You can see a little more of that red edge around the outside, and again, some of the different colors of the stars in the field of view. The Ring Nebula is a dying star that's used to be similar to our sun. So one day our sun might look like this, although we don't have to worry about that for another 5 billion years or so. And here's another. So these are 2 interesting nebula. I'll be, because the Ring Nebula is a dying star shedding its gas. And so dying stars are usually fairly small. It's a single star creating some gas around it, dying star nebulas, whereas star birth nebulas, like the lagoon cloud of gas and dust, are usually larger in the field of view, because these are huge star forming regions in our galaxy. And if we could, if we could see them, if our eyes were sensitive enough, if our pupils were as big as our 6-inch telescope, and we could collect light for 60 seconds, these starbirth nebulas would be fairly big in the sky, as big as the full moon. So that's a nice lagoon nebula. Looks like Evan kind of overplayed the red image of his 3 images. Not quite sure exactly what happened. Again, if any of you are having these problems, you can, and you want to test it out, definitely attend one of the office hours. Here, Margaret has done a RGB of the Crab Nebula. Very nice, little maybe dim on your screen, but again, you can see that different colors of stars. And one of the things I'm noticing here, which I would be interested in investigating further, there seem to be some blue stars that don't have much red or green, and I'm not sure what's going on there, or whether this wasn't aligned quite perfectly. I'll have to figure that out. There's another beautiful Orion Nebula with that sort of greenish interior and reddish outside. Again, in the case of this glowing gas that's surrounding these hot stars, it's a little bit like a neon gas tube, where you put energy into the tube and the neon glows orange. Well, the energy is coming from these stars, and this gas on the outside is a lot of hydrogen, which glows kind of pinkish red. And there's also a lot of oxygen created in the interiors of stars that ends up in these big star clouds. And oxygen glows with kind of this greenish color. And that's true in that little ring nebula as well. Oh, here I see one of my favorite targets, Rhea. This is great. The Trifid Nebula, I really love as an RGB target because it has these contrasting colors. The nebula on the bottom, which is the reason for the Trifid Nebula's name, Trifid, these 3 dust lanes. It's kind of split in 3. That nebula is reddish. And that's because, again, of this glowing hydrogen that it's made of being energized by this central hot star. But this nebula up here is something astronomers call a reflection nebula. And it's not actually fluorescing like the hydrogen gases down here. It's scattering the light from this bright star, and it scatters blue light more than red light. The dust particles in this nebula preferentially scatter blue light. So this is why I love this Trifid Nebula, and I'm just giving you some background just to help you appreciate some of these images and the images that you explore. So this blue part of the Trifid Nebula is blue for the same reason our sky is blue. The particles of dust and molecules of gas in our atmosphere scatter blue light more than they do red, and so the sky is blue. And that's also why this little top nebula is blue. So you guys are doing great work. If you haven't had a chance to get your color image up, don't worry about it. I'm going to the key, though, to getting ready to implement with your kids is to make sure you do know how to make an RGB image, and so we hope that you'll be able to complete that challenge. And then the final element of training after today's webinar is for you to create a wiki page. We talked about how to do that on the last webinar. That contains your outline for how you think you'll implement with your students. And we'll talk during today's webinar about a few different kinds of scope and sequences that you might be interested in pursuing. Let's see. Following this webinar, Erica will actually be having a webinar on Friday, specifically about how to set up your student accounts for when you're ready to implement. Okay. And one of the things that she will ask you to do before we give you your student accounts is to fill out another survey as a post-workshop survey. All right. So today, I wanted to show you some more of the kind of activity guides, some of the activities that you can do with your students. And in particular, I wanted to focus on an activity called From Pixels to Pictures today. And we're going to demonstrate how to do this activity. And here is some results of a class that did the activity. But I'm actually going to stop sharing my screen and have us do the activity on my desk here and have Erica turn her camera around. So here's what you want to do. You want to find Erica's camera here in your set of cameras, and where the ... is, you want to click on that and click on pin video, the words pin video, because you're going to pin Erica's video large on your screen so that we can show you this activity. And I'm going to do that on my screen. All right. And okay, so Erica will come over here, and I realize I don't have my beans. Let me go get my keys. So Erica's going to kind of set her the camera up so you can see that I have an egg carton here. That's great. Yep. And I actually have a sister in the restaurant business, so I have a very big egg carton. But you can make a 6 by 6 unit just by using 3 egg cartons next to each other. This one we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. So 6 by 5. So the egg carton here, in this activity, the egg carton is representing the detector in the telescope. And guess what each pocket of for an egg is representing? If anybody wants to type that in the chat box, what each pocket is representing? Pixel, exactly. Okay. And so this is a modeling activity to help you and your students better understand how the detector of a digital telescope works. Also, and so I have some beams here, and these are going to represent photons or particles of light. Somebody doesn't see Erica's camera. Okay, so if you're looking at me and not the big picture of an egg carton on your screen, you want to click on Gallery View, and then click left and right, looking for the picture that has a giant picture, the image that has a giant picture of an egg carton on it, and you want to pin video on that. Okay, so all right. So in this activity, students in pairs or groups of 3 are asked to simulate the idea of an object shining, emitting photons, traveling light years through space until they get into the telescope and hit the detector. And so my hands are a little close here. If I'm an object shining, right? The light is going, I might be an object that has 2 bright spots that I'm shining. And then you see that the 2 areas over here and over here, which were the sources where the sources were focused, end up with lots more photons. The next part of the pixels to pixel activity asks students to represent how much light fell in each pixel in some way using colors, but they have to figure out whether they want a different color for 1 pixel, 2 pixel, 3 pixel, 4, or whether they want to use those brightness bands. So that one color represents anything with 0 to 3 beams in it. Another color represents anything from 4 to 6 beams, and so on. So to kind of give you a sense of how this works with students, Erica has made somewhere here. Okay, she shined her pixels here on this detector, if I have this right. And one of these keys, let's see, how am I going to do this here, represents the raw data. One of these visual keys represents the raw data that fell on the detector. And so my question for you, let's look at the raw data. Okay. Actually, I realize I have to spin my raw data around here. Wait a minute.
There you go.
There we go. All right. There's my raw data. Okay, and here are the 2 representations that came from Erica's raw data and another student's raw data. So can you figure out which of these representations, the one on the left or the one on the right, represents this raw data?
Already got a guess.
They already got a guess, right? Exactly. And so this activity helps students understand, and you can make the model. You can kind of extend the model. In this one, we only use 1 energy of photon. You could imagine, although it's very hard to do, that you could have some kind of filter that would let certain beams through that would represent red photons, and certain, and then the smaller beams would be red, and they'd get through the filter or something like that. But it's very hard to extend the model that way. This really helps get the idea. The more light falls on a pixel, the higher the pixel value, and that gets represented in your software as differing colors with different intensities, but the choice of color is arbitrary. There's those color maps, and you can, and here Erica has made her own color map to represent the numbers of pixel values. All right, so if I, hopefully people were able to find, don't get dizzy as Erica moves back to her seat. I'm going to share my screen again. And you can see here that students, here's their, they had little beads falling on their detector. They didn't have an egg carton. They used this kind of square grid. And they were representing the process of light falls on a pixel, it converts to a digital signal. You have to encode that digital signal in some way to send the information, and then decode that information in a color map that represents the different pixel values. The write-up for this activity is in the Educator portal. If we go back here, the underneath curricula in unit, where'd it go? There it is, Unit 7, Investigating the Technical World, From Pixel to Picture. So there's a write-up for teachers. There's a of how to do it. There's a student worksheet and detector worksheet, just like the one Erica worked on, to try and represent how that how the inside of the telescope works. So you might not choose to focus on image processing in terms of your students' understanding, but that's an activity that can help them, help you and your students understand it better. Another activity, and again, here's the inside of the actual telescope. This is the one in Arizona. I can tell by the ground in the background. So this is one of the micro-observatory telescopes opened up, and you can see that there are lots of circuits that are controlling this robot telescope. So the next activity we wanted to show you is using electronic circuit modules called Little Bits, and it's a set of design engineering challenges for students where they can put these circuits together to simulate subsystems in the, whoops, sorry about that, what happened? To simulate subsystems in the telescope. So these little bits are expensive if you're unfamiliar with them, but we have several. We have 3 workshop classroom sets of little bits that can work for up to 30 students or so, I think, that we loan to YouthAstroNet members. So when you have an implementation plan, you think you know when you're going to be doing YouthAstroNet with your students or your youth in an after-school program, and you have a date for when you think you might like to do these engineering design challenges, there's a form right on the portal to reserve a Little Bits kit, which we'll ship to you, and then with a that you ship back. So let's show you the Little Bits so you can see them in a little more detail. Once again, I'm going to stop sharing my screen and pin. You need to, once again, hit that gallery view, find Erica's camera and pin that, okay? And we'll take a look at some of these little bits. So Erica, you want to come over here? So this model that I have on my desk here, yeah, there we go. This model that I have on my desk is composed out of cardboard pieces, just a box and various cardboard pieces, and some of the little bits that actually a student who was interning with us put together to simulate the various aspects of the telescope all together. And this is, he's got a base of the telescope that can aim left and right. He wasn't able to put this on a motor, but I think we have this on a motor, and I'm going to show you. So here is a circuit. The little bits, there's always a power supply, and then here's a little solenoid motor. I'm going to turn it on. Oh, we don't have a switch for that. In the wrong spot, that's why. Nope. There you go. Thank you. Quick one of the
you got to put it between the two, Mary.
Yeah. I gotta switch. One of the things you can notice is that these are very easy pieces to put together. So inputs that control what follows them are always pink, and outputs that make something happen are always green. And this input is a slider. And here I'm adjusting how far up, where the telescope is pointing in the sky. So one of the design challenges is, how do you create a motor or a system that can point up and down to target something in the sky? And so imagine this is actually the light sensor, which I'm going to show you next. And so I'm trying to aim it by adjusting this motor. But now the next subsystem is the actual sensor. And so this bit here, which I'm going to turn around so you can see it here. All right, this bit right here is a light sensor. Let's put this, put that down further. There we go. The light sensor. And I have a power supply for the light sensor. And then coming out of the light sensor, I have a little digital readout. Okay. So one of the design challenges is, can you create a sensor like a telescope's detector that can measure the amount of light it's receiving? And so if I turn on the power supply, which are these 9-volt batteries, here, turning on the power supply for my sensor. There we go. All right. And if you look at the digital readout, when I cover up the sensor, it goes down to, I guess you're seeing it upside down here, but anyway. As I cover up, let more or less light in, we're reading out different values. And this really is kind of like a 1-pixel detector. Now you notice that while the sensor is reading the amount of light, Erica is controlling a third little bit circuit that is operating the shutter. When students put in that exposure control, they are controlling how long the shutter stays open and closed. And so that's another design engineering challenge that's in the YouthAstroNet curricula. How do you create a motor that will turn a shutter on and off to block light and let light through? So these are all engineering design challenges. Again, all these bits come in a nice kit where they're all, we don't have an example of the kit here, but we ship it to you in like a little suitcase. And that's another way to focus your curriculum. Thank you for turning off all my circuits there.
Sorry for making you sick for a second.
It's going to make you dizzy for a second, and I'm going to go back to sharing my screen. There we go. So let's see. What I wanted to do now is show you a series of kind of potential scope and sequences that you could think about in terms of implementing with students. So I'm here in the YouthAstroNet Educators portal. Again, when you get ready to implement, this is going to be, Erica's going to go over all this in a webinar on Friday.
And there's a place in there, just like you said, for requesting the little bits. It's right in that section as well.
Right. Erica points out that right in this section, is it in the
down
material?
to more. Resource request form.
Resource request form. So if I click on that, if you'd like to borrow either the little bits or we also have a set of laptops which we can loan to you for up to 2 weeks. You fill out your information and when you want this, and then you're in the queue, and Erica will email you back about the availability of the resource. So again, we have a lot of support for you to implement all these projects. The thing I wanted to point out is YouthAstroNet is very adaptable. As we've been discussing with you, the core elements are basically learning to control the telescopes, learning to process images, and then using those resources to pursue some kind of project. And that project can be an astrophotography exhibit, it can be a presentation about what you've learned, it can be any kind of capstone project that you can imagine. I wanted to highlight 4 separate emphases that you might be thinking about and where resources are specifically for that. If you really wanted to focus on astronomy, you're in 5th grade and astronomy is one of your units and kids have to do moon phases or something like that, under YouthAstroNet curricula, actually, some key resources would be Investigating the Moon, Unit 6, and Astronomy Investigations, which also includes size and scale. Maybe you want to measure the size and scale of objects in the universe, as we talked about. Actually, another resource for this is our Micro Observatory Monday webinars. We just had one yesterday where we really went into detail about how to use JS9 to measure the size and scale of objects that you've taken a picture of. So if you're focusing on some astronomy investigation with the moon, or maybe it's life cycle of stars, or maybe it's the solar system, and you want kids to take pictures of objects in the solar system and create a display, information for that is here in Unit 8. And also, if I go back to the main page of the portal under Curriculum and Implementation Materials, here under Useful Resources, there's images of the telescopes, and in particular, this cosmic cast of characters. Oh, I have to, okay, cosmic cast of characters. Handout is really good for understanding kind of the 4 categories of astronomical objects that you can take images of with Micro Observatory. There's planets and moons, the bit players, as I call them, things that don't glow on their own, that don't shine invisible light, but that reflect the light of the sun, are planets and moons. Then there's stars, and we have lots of objects that have lots of stars or star clusters in the field of view. Then there's nebula, and so the cosmic cast of characters really helps students learn what these different things are and what they should know about to observe them. Another resource in that folder is this telescope observation log sheet, and that's really good to get kids to keep records of what they've taken images of. Of course, they have their own archive in their YouthAstroNet portal, but here they can keep notes after the image comes back about how it came out. Was it cloudy that night? Do they have questions about the image? And so it's a little log sheet for continuing observations. These 3 PDFs about the various targets give a little beginning information about the galaxies, the solar system objects, and the stars and nebula that are there. So that's an astronomy scope and sequence you could do. The final capstone could either be a project about the moon's phases or illustration of life cycles of stars or something about the solar system. That would be up to you. Another emphasis you might want to do, especially since we just talked to you about the little bits, is around telescopes and how the robotic telescopes work. And so again, under the curriculum materials, there are a number of resources for learning about the micro-observatory telescopes. There's an activity to compare your eye in a telescope, in particular, the difference between the aperture of your eye, which is 1/4 of an inch, and the aperture, the opening of micro-observatory, which is about 6 inches. There's also an activity in here, Unit 3, Introduction to Telescopes, called Kinesthetic Telescope, and it's one of my favorites. In this activity, students represent photons traveling from, one student represents the object in space, a bunch of students represent photons traveling, emitted by the object in space. A couple of students represent the aperture, the opening of the telescope. Another student represents the shutter, letting light through and stopping the light. And so it's a great activity to really understand how telescopes, the main feature of a telescope is that it collects light. And the bigger the opening, the more light it can collect, and the longer the exposure time, the more light it can collect. So this activity is a nice one to do if you were emphasizing telescopes. The students could show a variety of objects that were viewed through the telescope. Finally, a third theme that you might want to investigate in your implementation is image processing. And for that, you'd use the pixel to pictures that we just did. Perhaps have kids make a model of how a CCD detector works. Have them produce images that show various features of image processing. And that there are some activity sheets in Unit 2 here around understanding image processing. So, and then finally, you might choose to emphasize light and color, as we did on Friday, and do the Alien Eyes activity, which is in the Useful Resources folder. Alien Eyes was developed by one of our partner organizations, the Astronomical Society Pacific, so it's not in the YouthAstroNet curricula, it's in the Useful Resources folder, this Alien Eyes activity, which you remember we did with the colored trees in webinar number 2. So those are various emphases that you can have in your YouthAstroNet implementation. There's lots more you can do. I want to make sure you check out what other educators have done. You can see that both on the, if you look at the Educator Capstone projects, you can learn from other educators what they had planned to do. And your end project, your capstone project for completing this training that we've been doing over the last 2 weeks is to go to this Educator Capstone Project Wiki and create a page. And here would be my page. Mary, whoops, I remember I have to do bracket, bracket to create a wiki page. Mary installed ideas for implementation. Bracket, bracket, whoops, bracket, bracket. And I save that. And then I would create my page and edit. My ideas for implementation. And I think I'll do kinesthetic telescope and lots of other things, which I would write down and make some images.
Yeah, and there's 4 prompts at the top of that
yes,
page.
So thanks. Yeah. Go ahead.
Oh, so there's 4 prompts at the top of that page to help you kind of think about your implementation, what you're looking for, things you've tried out, just to give us an idea of what you're doing, and we'll comment back and give you more suggestions if you want.
Great. Okay. So that's kind of all the things we wanted to go through during this webinar, unless there are specific questions or difficulties you guys have been having or things you want to figure out how to do. So we kind of left some time here for if any of you have tried doing some images and had any trouble, let us know. Otherwise, you can keep working on your technique, and then when you encounter a problem, you can come to one of the office hours to figure out what happened. Are there any questions about what's going on here? And feel free to unmute yourself if you want to ask verbally rather than write in the chat box. What time are the requested images? Ah, great question, Ginny. Yeah, we seem to have some software potential little glitch about that this week that we're looking into, but when you're in the YouthAstroNet portal, the activity portal, and you make a request, if I make a request for the moon, normal view, 60 seconds gray filter, oops. 60 seconds for the moon, 0.1 second for the moon, there we go. So this request should get filled within the next 24 hours. Typically, they get posted at 9 a.m. or actually a little after 9 a.m. Between 9 and 9:20 a.m. They should wind up in your account. You can see we had a telescope failure here over the weekend, but typically, and here's images I asked for last week, and they came in. You can see, if I open this up a little bit, you can see that I requested them on the 18th, and the date of all these images is the 19th, early in the day, and these got posted at 9 a.m. So Ginny, you really want to encourage your kids to ask, potentially, to go to their YouthAstroNet portal every day and ask for more images and keep asking, so that they'll kind of always have the opportunity to have fresh images where the weather was good. So that's one of the tips and tricks, is to request images early and often. Other questions people have about how the telescopes work? Yeah, okay. So if you have an early morning class, right? You want to start requesting those and plan on your first day after, or maybe your first 2 days even, since kids will just request. You probably want to plan on using some of the archived images, and actually we're about to add more over here that will always be there, even if in your list you don't have anything yet. So, so that's one way to deal with, you have your students with you and their images haven't loaded into their accounts yet. You can use the archived images. There is also, and we showed this in yesterday's Micro Observatory Monday webinar, which again is available through your Educators portal. There is a way to get to the main archive of the Micro Observatory telescopes, and actually, if I go back to my image request form here, get images I requested. So this link here, here's all my images. This link is to our Micro Observatory image directory. And that directory is a web page that has thousands of images from the last 30 days of requests. And they're organized from the most recent down. So sometimes even before the images hit your students' accounts, you can find images in that image directory. If I click on this link right now, I get to that specific image of the Crab Nebula that I had asked for. And if I then go to this recent image directory, you'll see that I'm on a web page with thousands of images, and you can sort by object if you're looking for a particular object. Let's say I wanted the moon. Oh, I guess I have all my numbered objects. Here's all the Andromeda galaxies. Here's all the beehives. Here's all the crab nebulas. And let's say I wanted a crab nebula. There's one. You can actually drag and drop these images from the archive into JS9. So if I have a JS9 window open, click on Robotic Tools, JS9, and I have one of these images from the Micro Observatory directory open. All I have to do is sorry, I'm having a little trouble here. Drag this FITS image. Remember JS9, you want the raw data, which is the file with a special format called FITS. So I drag that right onto my JS9, and it will open that image in the image processor, and I can process from there. So again, that's another technique to get more images. Is there a good source for figuring out what is happening in these nebulas? Great question. Right in the YouthAstroNet activity portal, I go back, let me go here. Down on the right, you're going to see Astro Images, and the top link is to the site Astronomy Picture of the Day, which is one of my go-to resources for kids. So today's image is actually a periodic, where the elements came from. But at this website, Astronomy Picture of the Day, you can search down here for any target. And so let's say I wanted to know about the Crab Nebula. I'll type in Crab Nebula, and it gives me all these versions of the Crab Nebula that tell me something about it. So here's a Hubble image of the Crab Nebula. It's the mess that's left when a star explodes, and it tells me all about it. So that Astronomy Picture of the Day, these Astro Images links, this one is, I think, yesterday's Astronomy Picture of the Day. Yep, October 23rd. This is, I don't know if you guys heard the news about the colliding neutron stars that were discovered recently. This is the discovery image of the light that from that galaxy. Unfortunately, this galaxy is really far away. We can't really get a good image of it using micro observatories. So, your question, Ginny, prompts me to, yeah, the collision has definitely been a topic of conversation, right? So it's very exciting, certainly around here at the observatory. Everybody's all in a state of excitement over this discovery. Your comment, in fact, Erica and I were talking about this earlier today. I think what we might add to the Youth Astronet activity page is a little area that's called kind of research resources for kids to look up good websites that are for them to find out information about astronomy. There's a couple good ones we know of from NASA that I would definitely recommend, and I'll put links directly to those right in the Youth Astronet portal. So I appreciate that question, Jenny. Good. Other questions? And again, you guys, when you come up with ideas and suggestions, you definitely improve the portal for others. So that just like, you know, Jenny's suggestion, where can I find out more about these objects? We realize we need to make that more convenient for you. All right. Well, if there are no further questions now, remember that you can always use the forums on the portal to ask us more information. You can attend the live office hours, which are.
Oh, just ask another question.
Is there a place we can find written instructions for image taking or processing? Yes. Yes. There's video instructions for them, as you already know, in their portal here where it says tutorials and other useful videos. So there's video tutorials about how to request an image, how to process an image, how to create a true color image, how to create a wiki page, and how to use the region tools in JS9. And we'll be adding to these as we go along. So there's video tutorials, but you've asked about written instructions, and those are in the Educator portal. We go back there, and we go down into the curriculum and implementation materials. And so here, under a folder called Student Data Collection Sheets and Worksheets, are all the things that you would print out specifically for students. And I think there's one about imaging. Image processing, here it is. So this sheet is written instructions for how to open an image and how to experiment with the low brightness limit and high brightness limit sliders and how to use it. Thank you for that question. That was good. All right. Well, it's been great to have you guys online for webinar number 3. Again, we'll keep in touch via the portal. The next webinar, I don't think we have that in our slideshow, is, wait, is it on the portal? Mm-hmm. Okay, our next webinar, upcoming events.
Actually, if you go to the top center, webinar and schedule and office hours.
Webinar schedule and office hours. Here we are. There we go. So today is the 24th. We just had webinar 3. On the 27th, Friday, there's this optional time to interact directly with Erica around signing your students up. And office hours are regularly, at least for the next little bit while you guys are setting up, Tuesdays. So today, right now, in a few minutes, I'm going to log off and Harry will be logging on. And if you need some personal help, he'll be on for office hours. Wednesdays, 12:30 Eastern Time and 4 Eastern Time. And Thursdays, 12:30 Eastern Time. So these are the time for live office hours when you can just be one-on-one with one of the team here to address any issues that you're having. Okay. Well, you guys have been great. Thank you so much. And I'm really looking forward to seeing how you're going to implement with your students. We know that this is a learning process, right? It's your first time using all these tools. You have a lot to juggle to figure out how to implement with students. And we really want to be here for you to help support getting that done and help you have the least number of barriers so that you can really advance in learning using these tools. Great. I'm going to end the webinar here. I'll stop the